Hi, everyone. Welcome back. This is Earth and Space Science 101, Lecture 12, and the beginning of our next unit on water on Earth. So everything in this unit, Lectures 12 through 19, is going to in some way relate to water on Earth, or in one case, a fluid on Earth. We'll also stick oil and gas in this lecture, or in this unit as well, for reasons I'll go into a little bit later. So water is going to be a big, important part of Louisiana geology. So we're going to be able to actually bring in some local geology into this unit. We're going to do multiple lectures on rivers and multiple lectures on groundwater. But first, we're going to start off with a couple of lectures that are mainly going to be on oceans. So to get us started, I want to give you a little bit of a breakdown on where we find water on Earth. And the vast majority of water on Earth is obviously going to be in the oceans. So it's going to be in the form of salt water. It's not going to be fresh water. The first graphic that you're going to see kind of gives you a little bit of an idea of the breakdown here. Of all of the water on Earth, 97% of it exists in the oceans, with the remaining 3% being freshwater, existing in rivers, lakes, streams, and in the groundwater system, and in the polar ice caps in the form of glaciers. The most abundant place where we actually have fresh water is in those polar ice caps. It's actually twice as abundant to find fresh water in the polar ice caps and in the form of glaciers, so frozen water. It's twice as abundant to find it there as it is to find it in all of the groundwater and rivers and lakes on Earth. So as we break that down a little bit more specifically, we see that, again, over 97% of the water on Earth is in the form of the oceans. A little over 2% of the water on Earth is in the ice caps and the glaciers, with the remaining, actually less than 1% being in all of the groundwater, rivers, lakes, inland seas, and that tiny, tiny little bit that you have in the atmosphere. So water exists in all of these different places because of the water cycle. And that's going to be a big sort of overarching concept that's going to follow us throughout this entire unit. You really have to understand the water cycle and how critical it is to geology on Earth. So the water cycle is also called the hydrologic cycle. It's the same thing. It's the transfer of water through all of these different reservoirs, being the oceans, groundwater, rivers, lakes, ice, and in the atmosphere. So the oceans are going to be very, very important for the water cycle, for the hydrologic cycle, because they're the sort of ultimate source of all of the water on Earth. It's where 97% of the water on Earth resides. So all of this water is really essentially sort of starting in the ocean. So that's where we're going to start our sort of short little tour of the water cycle. We're going to start it in the oceans and start by looking how water comes out of the oceans and moves onto the land ultimately. So the very first part of the water cycle is the evaporation part of the water cycle. This is how water is going to go from in the oceans to into the Earth's atmosphere. And evaporation is just a blanket term for when a material moves from a liquid state to a gaseous state. The reason why evaporation is going to be most common on Earth for water is because obviously water is that compound that on Earth is found at that temperature that easily kind of goes from a solid to a liquid to a gas. Its range of temperatures in a liquid state is most compatible to the Earth's surface and the Earth's surface temperatures and pressures. On other planets like some of the gas giants and most notably the moons of the gas giants, you actually see different compounds existing in a liquid state and different sort of versions of the hydrologic cycle on those planets. On Titan, you have rivers of ethane and methane instead of water because it's much, much colder on that moon. So on Earth, again, it's mainly water. We're concerned with water. This is the water cycle. So evaporation is that part of the water cycle where water turns into a gas. Now, when this happens, when water evaporates, You are putting something into the Earth's atmosphere that's less dense than the other dry components of the atmosphere, like the nitrogen and the oxygen. It doesn't weigh as much. And so therefore, the water vapor immediately wants to rise up off the surface and move up into the upper atmosphere. When it moves up into the upper atmosphere, it encounters a part of the Earth's atmosphere that's colder than it is on the surface. And that cold temperature forces that evaporation to reverse itself. That brings us to the next step in the hydrologic cycle, and that's called condensation. Condensation is the process of taking a gas and turning it back into a liquid. And such as evaporation requires warmer temperatures to happen, condensation requires cooler temperatures to happen. So up in the upper atmosphere where it's colder, close to around a mile off the surface of the Earth, that's where condensation is most commonly going to occur. So then that water vapor turns back into a liquid and clouds form. But it's very important to recognize and to remember that clouds can't form, water vapor can't condense in the Earth's atmosphere without something to condense on. On the surface of the Earth, that happens on cold, solid surfaces at really early times in the morning, and we call it dew. In the upper atmosphere, those tiny little particles of salt and ash and dust that get up into the upper atmosphere, they provide a surface for that water vapor to condense on. So when that happens, you form a teeny, teeny, tiny little drop of water that's actually too light to fall down to the Earth's surface. As that drop becomes bigger and bigger and more condensation occurs, you're going to finally get a particle that's going to be too big to exist up in the upper atmosphere, and it's eventually going to feel the effect of gravity and fall back down to Earth. So we call that precipitation. Precipitation is going to take the form of either rain or snow, depending on mainly conditions on the surface of the Earth. Most precipitation actually starts off as snow. So in a sense, like even in Louisiana, it's always snowing. But before that snow actually reaches the surface of the Earth, it's going to melt on its way down. And then we actually experience this as rain. If that snow actually maintains low temperatures, less than 32 degrees Fahrenheit, all the way down to the Earth's surface, what you ultimately get on the surface of the Earth is snow. So this is the part, now that we've actually gotten that precipitation down to the ground surface, and occasionally that's going to be on the continents on Earth, this is where it has the potential to actually affect geology on Earth. So this is where runoff and infiltration is going to occur. And there's a reason why I've put a little star, a little asterisk next to these 2 points, because these are the 2 points that we're going to look at in a lot of detail in future lectures. We're going to look at the effect of runoff, and that's when all of this water that pools up onto the surface is going to occur too fast to infiltrate into the subsurface. And so then it runs off on the surface, it moves along the surface. When it's still in a solid form, and this movement is going to be the movement of ice, we call these glaciers. Glaciers are just basically solid, slow-moving rivers. If this runoff is going to take the form of a liquid, then we call these features rivers or streams or creeks. You know, any surface water that's going to be confined to a channel that's running downhill is going to be essentially a stream. Now, the thing about this is that these streams have the capacity to affect geology. They have the capacity to erode and deposit sediment. They have the capacity to carve canyons and do all this kind of cool things to the geology on Earth, but only until that water returns back to sea level. So it's gravity, it's being above sea level that gives the water, or in some cases the ice, the power to reshape the Earth. But once all that water moves all the way back down to base level again, it no longer has that power. And that's why a tremendous amount of sediment is deposited at the mouth or the end of streams, where all of that water is going to lose its capacity to keep moving sediment. That's how deltas, like the Mississippi River Delta out in the Gulf of Mexico, form. So that's what happens when this water or this ice is moving across the surface. If the water, in this case, is going to be precipitated onto the surface a little bit more slowly and evenly, then the subsurface can accumulate this water and soak it up like a sponge. So this is the part of the water cycle that we call infiltration. Infiltration into the groundwater system is going to occur with precipitation onto the surface, and then all that water is going to, or not all, but most of that water is going to soak down through the layers. It's going to percolate down through the layers, kind of like water in a coffee filter, and then ultimately reach some point in the subsurface that's completely saturated with water. And then, just like surface water, that groundwater is going to move down gradient, downhill in a sense. So that water in the groundwater system is going to move just like surface water does, just a lot more slowly. So it's really important to remember that groundwater doesn't really exist in these stagnant lakes underground. It's something that's dynamic. It's still moving, much like surface water does, and it's part of the overall water cycle. So once all of the surface water is going to make its way down rivers and down streams and through the groundwater system, it ultimately returns back to the oceans, thus completing the water cycle. Okay, so that's going to catch us up on the water cycle. The next thing that we're going to go into is water itself. And there's another name that you could give to the water molecule if you really wanted to, particularly if you're a chemist with a sense of humor. You could call water dihydrogen monoxide. And chemically speaking, it's basically the same thing as calling it water. It's still the same thing. It's still H2O. But here's a little warning label about dihydrogen monoxide, and something to maybe take into account whenever you see water warning labels in the future with some sort of chemical. All of these things are completely true about the water molecule, about dihydrogen monoxide, H2O. Dihydrogen monoxide is colorless and odorless. Accidental inhalation of dihydrogen monoxide, or DHMO, may be fatal. Prolonged exposure to its solid form, ice, causes severe tissue damage. Symptoms of DHMO ingestion can include excessive sweating and urination, a possible bloating feeling, nausea, vomiting, and body electrolyte imbalance. All of those really, really scary things are really basically just talking about water. So dihydrogen monoxide, water, same thing. But now we're actually going to look at how it's going to affect geology. We're going to look at how it's going to affect the chemistry of the oceans and why water is essentially sort of the universal solvent on Earth. Dihydrogen monoxide, again, it's the same thing as water, is a universal solvent because its structure is a polar structure. Anything that's a polar structure just basically has a positively charged and negatively charged aspect. So in dihydrogen, so two hydrogens, the two hydrogens are the part of that structure that are positively charged. The oxygen is going to be the part of the structure that's negatively charged. So that means that you can take any other structure, any other ionic structure, and it's going to relate to the polar structure of the water molecule, and it's going to make it easy to break those bonds. So you can take something that is ionically bonded, and our example of this is going to be salt, table salt, halite, sodium chloride, and we're going to see how it is ionically dissolved by the water molecule. So you can see how in our example here, you've essentially taken chloride and broken it off the structure of the rest of the halite molecule with all of those sodium and chloride stacked up very nicely, very, very cubically. We've broken off the little green molecule here, the chloride, and it's surrounded by all of these polar water molecules. So what's happening here is the chloride's negatively charged, and the part of the water molecule that's facing the chloride is positively charged. So it allows the chloride to be isolated from the rest of the halite molecule, and therefore it stays dissolved in the water. So when you throw salt into a pot of boiling water to dissolve that salt into the water to maybe make soup, or if you're trying to season spaghetti or something, the reason why that salt is dissolving into the water is because of the polar nature of the water itself. And so this means that because water has this ability to dissolve these minerals, it means that the salinity of water on Earth is going to really sort of, in a sense, increase over time, because exposure between the rock on Earth, especially those ionically bonded minerals within the rock, and the water itself is going to release some of those minerals and release some of those individual elements into the water. So one way of referring to the saltiness of water, how much dissolved halite and other minerals that water contains, is to refer to its salinity. So for our purposes, if I say total dissolved solids or salinity or saltiness, all those terms are basically interchangeable for us. It's just a measure of how much dissolved stuff, dissolved minerals, there is in the water. So I've got a little bit of a breakdown for you, very sort of simple breakdown of what the salinity of various waters on Earth actually look like. And it would be easy to think of fresh water as having absolutely no dissolved solids, but it always contains a little bit. All naturally occurring waters on Earth contain at least a small amount of dissolved content. So fresh waters like rivers, lakes, and the shallow groundwater system all contain roughly less than 1 gram per liter of total dissolved solids, or 1 gram per liter of total salinity. That would be the same as saying it contains less than 1,000 milligrams per liter. So in terms of how this would actually taste, you wouldn't actually really be able to taste the salt so much, but most tap water contains less than 200 or 300 milligrams per liter of total dissolved solid. It always has to contain some. That's sort of an interesting side note here. Even bottled water isn't completely free of total dissolved solids, because if you were drinking distilled water, as that water moved through your body, it would actually leach out minerals. It would actually be bad for you. So you need a certain amount of mineral content in your water. So again, fresh water contains less than 1 gram per liter. Seawater or salt water in the oceans contains between 30 and 50 grams per liter. And brackish water is really almost anything in between. It's an intermediate category. It doesn't have a very specific connotation. A lot of the deep groundwater on Earth is actually saltier than seawater. In some cases, 4 or 5 times the salinity of seawater. Under these pressures, it's possible to get a lot more salt into the water than it is at surface conditions. So the salinity of seawater in most of these naturally occurring salty environments on Earth is going to be a range of minerals, the most abundant of which are the elements that make up the mineral halite. So when you dissolve halite, it's just sodium chloride, and those two make up over 80%, 85% of all of seawater, with everything else that you find in seawater making up that less than 15% or so. So the sulfate, magnesium, potassium, calcium, and some other things like carbonate in seawater, they all make up less than 15% of the dissolved content in seawater. So seawater salinity actually varies with its position on Earth. In the polar regions, it's actually much lower than it is closer to the equator, and that all has to do with temperature. At higher temperatures, it's possible to dissolve more salt into seawater. As you might have kind of guessed, it's pretty intuitive when you compare it to something like taking boiling water and throwing salt in it versus cold water and trying to dissolve salt in it. So the seawater salinity is going to be greater in the equatorial regions where it's warmer, less so in the polar regions. And then it kind of varies a little bit on Earth also due to where the ocean currents are, because ocean currents are going to carry warm water away from the equators and towards the poles. So salinity, as we're going to find out in a little bit, is actually a really important part of what is going to cause the water on Earth to circulate, both on the surface and with depth. Because the salinity varies with its position in the oceans, it's going to cause differences in density, and that difference in density is going to cause the seawater to circulate. But before we get into ocean currents in any more detail, I want to first go into why seawater is salty, some potential sources of salinity. Now, to make sense of this, let's kind of think about Earth as it was billions of years ago, when the Earth was newly formed and when the oceans were newly formed. We think the oceans formed at some point in the first 500 million years of Earth history. So right at about 4 billion years ago, we had oceans on Earth. In fact, most of the Earth's surface was covered in oceans at that point. The oceans at that time probably weren't salty. All of our geochemical indicators at that time of what the salinity looked like in the seawater would suggest that water was mainly fresh water. It was similar to lakes and rivers today. The oceans became salty over time because of some of these geological processes involving the water cycle and involving plate tectonics. So one source of salinity is essentially just the water cycle. And let's think about it like this. As water is moving out of the oceans and into the Earth's atmosphere, you're just evaporating out the water. You're not evaporating out the salt as well. Then that water precipitates onto the surface of the continents, where it flows across the continents, or in some cases flows through the groundwater system. Either way, it's going to have rock and mineral interactions, where all that water is flowing through these minerals and dissolving out some of that content and the salts and all that kind of stuff. So then all of that material that's dissolved into the water then moves back into the oceans again. So essentially, with every run of the water cycle, you're delivering more and more salt into the oceans. So this doesn't make a big difference over a year or even 1,000 years, but over the hundreds of millions and billions of years of Earth history, it has caused the seawater to increase in salinity over time. And some of these minerals have very few ways of coming back out of the seawater, precipitating out of the seawater, the most notable of which is sodium and chloride. Some of the other dissolved constituents of seawater, like sulfate and carbonate, they have fairly easy ways of precipitating out of seawater, but sodium and chloride don't. Therefore, they are the most common components of seawater besides the water itself. So one source of salinity is the dissolution of minerals on the continents being driven to the seas by the water cycle. The second one is one that you probably wouldn't really think of. You don't really think of plate tectonics and seawater salinity as having a lot of things in common. But as it turns out, at mid-ocean ridges, where the crust is very, very thin, where the plates are pulling apart, it's actually possible to get some circulation of seawater into the Earth's crust and then back out again at these mid-ocean ridges. So you get all of this hydrothermal circulation. You get this water that's being pushed into the crust of the Earth itself. It's heating up. As it heats up, of course, it's going to dissolve minerals. And then it's ejected back out into the oceans in these sort of submarine hot springs, in these essentially sort of geysers that exist along with all this volcanic activity at the divergent plate boundaries, at the mid-ocean ridges themselves. So mid-ocean ridges are a second equally important source of salinity for oceans on Earth. Okay, so now that we've talked about the salinity of the oceans, I'm going to do a little, very, very brief recap of where the oceans of the world exist. This should be primarily review. So what we're going to do to kind of add a little bit of twist is look at the oceans of the Earth from a plate tectonics perspective. No, in Unit 1, we covered plate tectonics, but I didn't do a whole lot on the plate tectonics of the ocean floor because I knew I would be covering it a little bit later. I'd be covering it now. So we're going to go from largest to smallest through the 5 oceans of the world. The biggest, of course, the most important ocean of the world is the Pacific Ocean. The Pacific Ocean is going to be very important from a plate tectonic standpoint because it's essentially completely encircled by convergent plate boundaries where parts of that Pacific plate are subducting underneath the continents. So this leads to the formation of trenches, and it leads to an extensive amount of volcanic activity and earthquakes. So that's why they call the border of the Pacific Ocean the Ring of Fire, because of its relationship between the ocean floor and plate tectonics. One place where the ocean floor is subducting down underneath a continental landmass is forming the Mariana Islands is a place called the Mariana Trench. And in the Mariana Trench, you're taking part of the Pacific plate, subducting it beneath, in this case, more oceanic crust that's sort of younger and more buoyant than the stuff that's subducting down. And along that boundary, where one plate is subducting underneath the other, you're creating this environment where those two plates are being pulled down, creating a trench on the ocean floor. The deepest point on that trench is called the Challenger Deep, and it's essentially the deepest point on Earth, 35,000 feet below sea level. So it's actually deeper below sea level than the highest point on Earth, Mount Everest. The second largest ocean on Earth, and also important from a plate tectonic standpoint, is the Atlantic Ocean. Now, unlike the Pacific Ocean that's ringed by these convergent plate boundaries where the plate is actually destroying itself, the mid-Atlantic ridge in the Atlantic Ocean is essentially free of any convergent plate boundaries. The Atlantic Ocean basically just formed because the New World and the Old World, in a sense, so North and South America, were splitting apart from Europe and Asia and Africa. Started 250 million years ago when Pangaea broke apart and continues to occur today. It just happens really slowly. So right down the middle of the Atlantic Ocean is a mid-Atlantic ridge, a mid-ocean ridge that is doing the work of really sort of pushing these continents apart and just creating this ocean in the gap. It's the longest mid-ocean ridge on Earth, but certainly not the only one. There are mid-ocean ridges in the Pacific and even in the Indian Ocean, as we'll see next. The Indian Ocean has a very interesting triple point where the mid-ocean ridge in the Atlantic Ocean is meeting up with this point where India is kind of slamming up into Asia. So it's a really interesting tectonic point on Earth. And the Indian Ocean in general is smaller and about as deep as the Atlantic Ocean. So now we're going to go to our last two oceans are going to be the polar oceans. We're going to go first to the North Pole and then the South Pole. The Arctic Ocean is distinguished from the rest of the oceans on Earth as essentially being that part of the ocean that's covered in a layer of ice year-round. Or at least at this point, still covered in a layer of ice. The future remains uncertain, and what we're considering to be the Arctic Ocean, that part that's covered in ice, is shrinking every year. So it's it's a lot less deep than the rest of the oceans on Earth. It's about a quarter of the overall depth of the Atlantic and the Pacific Oceans, and covered by that permanent layer of ice. The Arctic Ocean, as we'll find out a little bit later, is also really important. That exact temperature of the Arctic Ocean, it's really important for the ice ages that have plagued North America and Europe for around 2.5 million years. Fluctuations in the temperature of that ocean remain really important for the next ice age to come. The Southern Ocean is going to be that part of the ocean that's essentially encircling the continent of Antarctica. And it wasn't always designated as its own continent. If you're kind of scratching your head and thinking back to grade school and trying to think, like, did I learn this as one of my oceans? I remember Pacific, Atlantic, Indian. It may have not actually been an ocean at that point. But it is now, because we now understand that cold water currents basically encircle the continent of Antarctica and keep that cold water next to that continent, and it essentially doesn't allow warm water from the equatorial region to reach that part of the world. So essentially, that's one of the things that makes the South Pole a lot different than the North Pole, where warm water can get all the way up into the Arctic. So the Southern Ocean is its own thing, mainly because of the ocean currents that encircle that continent. So this is going to bring us around to talking about ocean currents again. And we've already talked about one thing that's going to cause ocean water to circulate, and that's going to be seawater salinity. But the other thing, that major thing that's going to cause seawater to circulate is going to be temperature. So it's temperature, salinity, and the rotation of the Earth and the Coriolis force. So as you can see on this first map of all of the ocean currents on Earth, there's a little bit of a mirror pattern between what's going on in the North Atlantic and North Pacific oceans. There's a mirror pattern between what's going on in the Northern Hemisphere and what's going on in the Southern Hemisphere. And that's because of the rotation of the Earth. It causes these things called gyres to form. And these gyres are a big driving force in your overall ocean current. It causes the water to rotate in these ocean basins. So the thing that's actually causing this to take place is the rotation of the Earth and something called the Coriolis force. It's essentially the same reason why hurricanes are going to want to rotate. Anything that is going to have to do with something moving a long distance across the surface of the Earth is going to be subjected to the Coriolis force. So in this case, it's going to be water on Earth. So you always have to kind of think about where all this water is wanting to move and then where it ultimately ends up because of the Earth's rotation. So if you were starting, let's say, at the North Pole, and you were looking at the journey of a single water molecule from the North Pole, and it's moving ultimately towards the equator, what would happen is that that water molecule is actually going to wind up somewhere to the right of its destination. So deflection occurs to the right in the Northern Hemisphere because the Earth itself is rotating to the east. Whatever's going to happen in the Northern Hemisphere is going to be reversed in the Southern Hemisphere. It's going to be sort of the mirror pattern. And deflection occurs to the left in the Southern Hemisphere. So then this drives the North Atlantic and the South Atlantic gyre, and it does the same thing in the North and South Pacific. We're going to have these warm water and cold water currents that are going to be the result of, first, the warm water being moved from the surface of the oceans close to the equatorial regions. It's going to get rotated around in this roughly clockwise motion in the northern hemisphere, get pushed up. Let's say we're talking about the North Atlantic gyre. It's going to get pushed up into the Gulf of Mexico, up the eastern seaboard, up close to the Arctic, where that warm water is then going to be replaced by cold water moving back down to the equator, down the coast of Europe and Africa. So this is going to be one thing that's going to cause oceans to circulate, is going to be that Coriolis force, that rotation. The secondary thing is going to be, of course, temperature and salinity, because that's going to cause the seawater to vary in density. Warm water that is going to be more fresh, less salty, less overall salinity, is going to be more lightweight. The deeper occurring cold water on Earth is going, especially if it's salty, is going to be more dense. And so anything that's salty or anything that's cold is going to want to sink. Anything that's warm or anything that's less salty is going to want to rise. And then that is going to cause seawater to circulate not just on the surface as affected by the Earth's rotation, but also to circulate with depth as well. So what all of this ultimately comes to, this effect of the Coriolis force, the Earth's rotation, and temperature and salinity, is that seawater is going to rotate around not just on the surface, but also with depth. And when we look at the effect of all of this, we find that seawater moves around on Earth in something called the global conveyor belt of ocean currents. And I like this idea of a conveyor belt because it ultimately sort of winds up back again where it starts. So if we follow the conveyor belt from the North Atlantic, you see that that starts as warm water moving into the Gulf of Mexico, up the eastern seaboard, and into the Arctic, where that water then starts to get cold. As it gets cold, it's going to sink. Then it goes down the eastern seaboard, down the, and it's still deep at this point, through the east coast of South America, next to Antarctica for a bit. It's going to come back around in the Pacific, go up the western Pacific, and then once it gets into the northern Pacific, it's going to warm up and then move back across the world's oceans, back through the Indian Ocean, back into the Atlantic, and then wind up back again where it started. So it follows through this entire cycle. And really important to remember, all of this is then affected by both temperature, salinity, and the Earth's rotation and the Coriolis force. So essentially, in a fairly brief way, that's ocean currents, or as much of it as we're going to get into in this class. So I thought it would be a really fun way to end this particular lecture by bringing you on a little field trip. So we're going to go ahead and cut to that now. Dr. Blanchard, thank you so much for coming out here and let me come out here on this trip and let me be part of this. So tell me what these things do.
These are conductivity meters.
Okay.
I'm going to put one in the ground right here, and it's going to stick in the ground. And there's actually 3 conductivity meters here. One that the ground level is going to be right here, and these openings right here let water in to here where there's 1 meter, and that's 10 centimeters deep, and then another one right here that's 20 centimeters deep, and another one right here that's 50 centimeters deep, and they are going to measure the conductivity at those different depths. The reason why we measure conductivity is that it is proportional to the amount of salt in the water. And that is the thing that's important for the environmental scientists. The amount of salt in the water, or the salinity, really determines what can grow out here. The salt levels here are higher than they were historically, so the plants that used to grow out here can't grow out here anymore.
So compared to other times that you've been out here putting these sensors in place, what does the water level look like right now? Is it relatively high?
This is about normal. The ground's usually not dry right here. There's usually water, standing water on the ground. Sometimes it'll come up to the top of this, but normally it's about like it is now.
So you talked a little bit about the relationship between conductivity and salinity. Can you go into that a little bit more, how those two properties are related to each other?
Yes, conductivity and salinity, the amount of salt in the water, the salt provides ions, and the ions allow electricity to conduct. So what we really do here is we apply an electrical voltage to two metal prongs. So right now, there's two metal prongs that are just hanging out in the air, but once we stick it in the water, the salt will allow an electrical current to flow through between those two prongs. And the amount of current that we get relative to the voltage that we get lets us determine the conductivity of the water, which lets us know how many ions are in there, so what the salinity is.
So you've had these sensors in place in the past. What have your historical results looked like, and how do you expect them to relate to the results you're going to get from this study?
We did have them out here for a trial run, and we actually was interesting what we saw. In the beginning, when we put them in, we saw about the same level of salinity at all depths, so the water was well mixed. But then over time, we saw a layer of fresh water come in, like maybe there was a heavy rain or something, and then the fresh water floated on top of the salt water. So even though there's fresh water, it only went down, and we could only see the fresh water at 10 centimeters. We didn't see it at 20 centimeters. So the fresh water, there was a freshwater layer that was only this deep, with salt water still underneath it. And that's the kind of thing that we're interested in seeing, is how the water mixes, how the fresh water and the salt water mixes.
So I think it's time to go ahead and actually do this experiment. So hopefully maybe you could show me how these things work now.
Certainly. Okay, let's see. Put them in the same place where they were before. So I've got this strap here to hold it in. That's my line right there for the dock. And there we go. Okay. We'll come back and do that later. All right, let's go put that one in at the very end of the boardwalk. Okay, but before we put that in, we're going to stop and take a water sample right here at this well. And this is to compare my readings with. We're going to get the salinity of water at this well to compare to my readings. That's how I'm going to calibrate my measurements. And one more water sample right here, because we're going to put that probe out at the end of the boardwalk right there. I can actually tell you what the salinity is out here, since you asked. It is 1.13, which is really on the low side of what we get out here.
Parts per thousand.
Parts per thousand,
Right.
yeah. And here we go. Ready? The battery chargers have little timers that determine how long it turns on once it gets dark, how long it runs for.
So were these wells already in place, or did you place these as part of the experiment?
No, these are Dr. Schaefer's wells from biology. He's been out here for years and years and years, taking measurements once a week. He has a student come once a week and drop a conductivity meter in there and make their own measurements, and that's what we're doing. We're doing the same kind of measurements just on a daily basis, and you know, if it's bad weather and no one can come out, we won't miss a measurement because the meters can work on their own. And plus, this just measures this gets water from about 5 centimeters depth down to about, I don't know how deep it goes, maybe about 75 centimeters depth. So it averages over that whole depth, and you can't see the stratification that we see. You can't see the difference between the fresh water on top and the salt water underneath. So that's the value that these probes are adding, is that you can see that those different layers of fresh water and salt water, and that's what we're trying to the kind of information we're trying to provide to Dr. Schaefer to help him with his plans to bring this marsh back to its historic state.